The title says it all. Avi Loeb 3 and Atlas stay in our solar system. Yes, that's right. 3 and Atlas could stay here. On the 29th of October 2025, it passes perihelion, and that day Earth will be on the opposite side of the sun. We're blind. And right then, according to Avi Loeb, it could pull off a silent trick. The overturn maneuver. Not speeding up, but slowing down and falling into a bound orbit invisible to us. Why is that scary? The signals are already strange. It's shown beyond Jupiter, showing a green glow way too early. It flies almost in the ecliptic plane, about 5 degrees. On October 3, it passes very close to Mars, about 18 million miles away, and its chemistry seems out of this world. The CO2 abundance is 8 times that of water, even the mass estimates. Around 33 billion tons match the initially estimated size. Too many coincidences forming a pattern. Yes, on October 29, behind the Sun, Atlas slows down and stays. It won't be a guest. It will be a neighbor. And then, the question is simple and terrifying. When it comes out from behind the Sunday, will we see a bound orbit? And if so, is it just a strange comet or an intelligent artifact that has decided to stay by our side? Let's start with the date, the 29th of October, 2025. It's no ordinary day on the calendar. It's perihelion, the closest point to the Sun, and that very day Earth will be on the other side of its orbit. We won't see anything. The Sun will be right between us and Atlas. Total darkness. Avi Loeb argues this isn't a coincidence. It's an opportunity, the chance to do what spacecraft have been doing for decades. A gravity assist maneuver, but in reverse. Not to speed up, but to slow down, shed energy, fall into a bound orbit, and stay here. Think about it. If you wanted to change trajectory without noise or witnesses, when would you do it? Exactly when no one can see you. When 93 million miles of blazing plasma hide you from every telescope on the planet. Still, better not get ahead of ourselves. First, it's worth reviewing why this idea came up. Why a serious astrophysicist from Harvard dares to say publicly it might not just be a rock. It all starts with the size. Initial estimates say about 12 miles in diameter, bigger than Manhattan, roughly twice the size of the asteroid, linked to the dinosaur extinction 66 million years ago. A colossal object. So colossal it's hard to see it as just any visitor. Loeb did the math. How much heavy matter floats in interstellar space? How many rocks does planet formation eject? What fraction of that passes near us? The answer is simple. An object this size should appear on average once every 10,000 years. Once every 10,000 years. And how long have we been systematically searching? Barely a few decades, maybe a bit more if you count the years, before modern detection techniques. And in that time, we've found something that statistically should only cross paths with us. Once per century. Century after century. Not impossible, but odd. And it doesn't end there. Before Atlas, we detected 2 interstellar visitors, Oumuamua in 2017 and Borisov in 2019, both small. Oumuamua was about 330 feet long, the size of a football field. Borisov, a few hundred meters, roughly the same order of magnitude. The size distribution in the universe follows a power law. Tiny fragments abound, giant blocks are rare. It's physics in planetary system formation. For every mountain ejected, there are billions of rocks. For every big rock, billions of pebbles. Statistically, we should have seen thousands of small objects before encountering a giant. Loeb calculates around 100,000 bodies the size of Oumuamua should have crossed paths with us before something like Atlas. 100,000, and we've seen 2. One might argue maybe our detection methods are biased. Maybe the big ones are actually harder to see. Atlas showed up first because it's bright and obvious. It's a reasonable argument with one caveat. Atlas shouldn't have been that bright. At the distance, it was discovered late July 2025, beyond Jupiter's orbit far away. Sunlight is weak at that distance. Most comets barely stand out. They're usually cold and inactive, ice and rock drifting, no coma. That bright cloud of gas and dust only forms when they get much closer to the Sunday. Many activate around 3 AU due to water sublimation, and some near 5 AU because of CO2. But Atlas was shining not a little, enough to catch attention immediately. Bright enough that early calculations assumed it must be huge to reflect so much light. It's like seeing a lantern lit in the middle of Antarctica. It shouldn't happen yet. Loeb emphasizes this. Comets usually need to get within a few astronomical units of the Sun to become active. Jupiter is over 5 AU away, and Atlas was even farther when it already stood out, unless, and here's the controversial idea, its brightness didn't depend on solar heating, unless it produced its own light. Let's take it step by step because the coincidences start piling up, one after another, until you wonder if coincidence is the right word. Next point, the trajectory. Here, the fine-tuning argument takes shape. When an interstellar object enters our system, it can come from any direction and any inclination. It doesn't have to respect the plane in which our planets orbit. That's our geometry, not theirs. A visitor from another star should arrive with a random inclination, unrelated to the ecliptic plane, the plane where our orbits lie. But Atlas doesn't behave that way. It arrives aligned with the ecliptic, within about 5 degrees, almost flat, a remarkable synchronicity with the orbits of Earth, Mars, Venus, and Jupiter. Loeb estimates the probability of such. A close alignment by pure chance at about 1 inch 500. Not impossible, but uncommon. Enough to raise an eyebrow, enough to take note. And there's more. Atlas not only aligns with the plane, its path takes it very close to several planets, very close. On October 3, in just a few days, it will pass about 18 million miles from Mars. Astronomically, that's a notable close approach enough for NASA's Mars Reconnaissance Orbiter to try photographing it with its high-resolution camera. But it doesn't stop there. Atlas also makes relatively close passes by Venus and Jupiter, 3 planets, all in orbital positions that coincide with the visitor's path. Loeb calculated the combined probability that a random interstellar object would pass that close to Jupiter, Mars, and Venus, just when those worlds are in the right part of their orbits. The result? 1 inch, 20,001. Think about that for a moment. We're no longer talking about a single rarity. We're talking about multiple overlapping rarities. Size, brightness, at distances where it shouldn't shine so much, alignment with the ecliptic, and close passes by 3 different planets. Each piece alone could be chalked up to chance, but altogether, Loeb uses an intuitive comparison. You can say each roll was luck, but if the same face comes up again and again, you start wondering if the dice are loaded. Then comes the central argument. If true, it would be the most uncomfortable hint of intent. Atlas will reach perihelion on October 29. That same day, Earth will be exactly on the opposite side of the Sunday. We won't be able to see it. Every Earth-based telescope will have the Sun. Right between us and the object, a solar conjunction, completely hidden. Loeb suggests that moment would be ideal for a trajectory change. If you wanted to use the Sun's gravity to slow down, turn, and get captured into orbit without being observed, that would be the time. Behind the Sun, out of our field of view. He calls it the overturn maneuver. Normally, spacecraft use the gravity assist to gain energy at the point of maximum speed near a massive body like the Sunday. A small push yields the biggest change in velocity, but the same principle can be applied in reverse. Fire engines to brake, lose energy, let gravity capture you into orbit. If Atlas did that on October 29, while we can't track it, it could effectively get trapped inside our system. It wouldn't just pass by like a typical visitor. It would stay, orbit the sun, come back again and again, remain in our neighborhood indefinitely. And the very timing that perihelion coinciding with its invisibility from Earth adds another layer of improbability. If we took Atlas's trajectory and randomly shifted its arrival by a few weeks, the chance that perihelion would fall exactly when Earth is on the opposite side of the sun would be low, not zero, but low. One more piece fitting together maybe too well. Now let's dive into the size problem. It's not just that Atlas is big. What matters is what that size implies for our understanding of interstellar objects, how often they should appear, what we should have detected before, and why the order of discoveries matters. When Loeb talks about a 12-mile estimate, he's starting from initial brightness calculations. The process is straightforward. Measure how much sunlight the object reflects, estimate the probable surface reflectivity, the albedo, and from there deduce the diameter needed to produce that reflected light. For Atlas, those first numbers converged on the same answer, about 12 miles. Loeb immediately flagged this as problematic, not because a 12-mile comet is impossible, there are some in our own system, but because encountering one so early in a relatively short search campaign with an interstellar visitor of that size breaks size distribution expectations. Here, cosmic debris statistics come into play. Whether asteroids, comets, or interstellar rocks, they usually follow a power law. For every large object, there are exponentially more small ones. If there's a 6-mile rock, there could be 100 1-mile rocks, 10,000 4-inch ones, and 1,000,000 33-foot ones. The numbers skyrocket as size decreases. This pattern appears everywhere in nature: lunar crater sizes, earthquake magnitudes, city population distributions. Big things are rare, small things are abundant. The universe doesn't make mountains at the same rate as pebbles. That's why when Loeb estimates the interstellar object reservoir, he expects the same pattern to hold. If the distribution follows this law, we should be drowning in tiny visitors before seeing a giant. Before crossing paths with something 12 miles across, we should have cataloged thousands, maybe tens of thousands of objects the size of Oumuamua, around 330 feet. But that hasn't happened. We've only found 2, Oumuamua and Borisov, both small, between a football field and a few hundred meters. And suddenly, Atlas appears, potentially 100 times bigger in diameter, implying thousands of times more volume. Loeb states firmly, given the limits of heavy element deposits in interstellar space, we should detect on the order of 100,000 objects the size of Oumuamua before finding an Atlas. 100,000, and so far, only 2 detections. From here, the argument splits. There are several possible readings of the discrepancy. One option: our methods are biased against small objects, and we only catch the big and bright ones. That's plausible. Telescopes have limits, and small, dark rocks easily slip through. Another, the initial size estimate is wrong. Maybe Atlas isn't really 12 miles across. Perhaps the brightness we saw didn't come from a gigantic solid core, but something else. A huge coma of gas and dust scattering light. In that case, the core would be much smaller, and the apparent brightness would come from an extended atmosphere. That's a reasonable explanation. Comets do that, developing comas tens or hundreds of thousands of kilometers wide, even with cores just a few kilometers across. But then another layer of the problem appears. If Atlas is so bright because of a massive coma, it means it's active. Its ice sublimates and ejects gas and dust. That implies solar heating, and if it's already active enough to show a large coma beyond Jupiter's orbit, 5 astronomical units where most comets remain cold, then we're talking about unusually high activity, much greater than typical at that distance. Why? What's heating it? Beyond 5 AU, solar radiation is weak. It falls off with the square of the distance. So at Jupiter's orbit, sunlight is 25 times less intense than on Earth, not much energy to sustain vigorous evaporation. So two main alternatives remain. Either Atlas contains extremely volatile ices, compounds that sublimate at very low temperatures like CO or CO2, something we saw in Borisov, or there's some additional energy source. Here, the green glow comes in. A few weeks ago, recent observations reported a strong green tint in Atlas's spectrum. In comets, that color usually comes from diatomic carbon, C2. Solar ultraviolet radiation breaks down complex organic molecules in the coma, producing these fragments that emit green light. That alone is normal, many comas are greenish. What's strange is the timing. The green appeared when Atlas was still too far away, beyond Jupiter, where solar radiation usually isn't strong enough to efficiently break down those complex molecules. At that distance, most comets are dark, cold, and inactive. Loeb points this out as another statistical anomaly, not impossible, but uncommon, another 6. Added to this are mass estimates, at least 33 billion tons. That sounds huge, yes, but it's worth putting in context. A 12-mile sphere, even with comet-like densities about 500 kilograms per cubic meter, should weigh around 1 trillion tons. That is, 2 European trillions, far above 33 billion. If the 33 billion figure is correct, it suggests a much smaller core or an extremely low density. If we really talked about 12 miles and rocky metallic materials, 3,000 to 5,000 kilograms per cubic meter, the mass would be even greater, not less. Something to verify with better data. In any case, if Atlas had an exceptionally high mass, for its apparent size, its gravitational pull on the surroundings should be measurable. Small perturbations in the orbits of Mars, Venus, or even Earth during close approaches. Detecting those would confirm the mass. Not detecting them would force a model revision. And back to the trajectory, it's not just the alignment with the ecliptic or the closeness to several planets, but the specific geometry of those passes. On October 3, not detecting them would force a review of the model, and the trajectory isn't just about alignment with the ecliptic or proximity to several planets, but the specific geometry of those flybys. October 3rd, Atlas will pass 29 million kilometers from Mars, about 1.9 AU for comparison. That's roughly 77 times the Earth-Moon distance, far on a human scale, close in orbital terms. What's interesting is the configuration. At the moment of closest approach, Mars will be at a specific point in its orbit, and Atlas will arrive at a certain inclination. It's not just any geometry, it allows for gravitational interaction, even if weak. Something similar will happen with Venus and Jupiter. Each encounter happens when the planet is in the right window of its orbit, so Atlas can receive or give a small gravitational nudge. Loeb recalculates the combined probability that a random visitor passes close to all three at just the right time. It's about 1 inch, 20,000, not an isolated rarity, but several stacked rarities. Size, brightness at distances where it shouldn't stand out, alignment with the ecliptic, and close passes by 3 worlds each piece alone. Admits a simple explanation, but altogether? Here, an intuitive comparison helps. You can claim luck again and again, but if the same face shows up on the dice roll after roll, eventually you wonder if they're loaded. Then there's the jet issue. If Atlas has a huge active coma, that gas escape acts like a tiny rocket engine, producing non-gravitational accelerations that shift its trajectory from what gravity alone would predict. Oumuamua showed a small but measurable deviation. One reason Loeb suggested a technological origin because that thrust didn't fit well with normal outgassing. Borisov, on the other hand, had a classic jet signature, a defined tail, clear spectral lines, and non-gravitational acceleration matching the model. And Atlas, so far, shows no conclusive sign of non-gravitational acceleration breaking the gravitational fit. That would be consistent with low activity, or an object without a strong jet. But if its brightness is due to a gigantic coma, why don't we see measurable thrust? Another point that doesn't quite fit. Loeb doesn't give a verdict. He raises questions. Why does the apparent size come out so large? Why does the brightness appear so early? Why the green color at an odd time? Why that estimated mass? Why such a finely tuned trajectory? Why no clear non-gravitational acceleration? Each doubt alone has possible explanations, but together they paint a picture that doesn't quite fit a simple model. And that leads us to the next layer: chemistry, the spectra. What Hubble and JWST recorded when breaking down Atlas's light, because if size and trajectory are already strange, the chemistry promises to be even stranger. Let's move on to chemistry. That's where things get really uncomfortable. When the Hubble Space Telescope and James Webb pointed at Atlas and broke its light into a spectrum, something appeared that shouldn't be there. Spectroscopy is essentially a fingerprint of matter. Different atoms and molecules absorb and emit light at specific wavelengths. By dispersing the object's light with a prism or a grating, you see which colors intensify and which fade, and from that pattern you can say, here's water, here's carbon monoxide, here's cyanide, here's sodium. In comets, the lineup is usually predictable. Water H2O dominates after all. They're dirty snowballs. Then comes carbon monoxide CO, carbon dioxide CO2, sometimes methane CH4, ammonia NH3, diatomic carbon C2, cyanogen CN, hydroxyl OH, the standard kit we've seen in dozens, even hundreds of comets. Spectra almost always look similar. Atlas, however, showed something else. The CO2 to H2O ratio was about 8.18 to 1. CO2 dominated. That's unusual, very unusual in the solar system. Most comets have ratios closer to 10 to 1 or 20 to 1 in favor of water. Water is the base. CO2 is the secondary. Even Borisov, the interstellar comet from 2019, showed water dominance. Its spectrum was familiar, reassuring like ours. Atlas, 8 parts CO2 to 1 part H2O. The ratio is flipped. Loeb points out another anomaly. If it comes from another system, maybe that protoplanetary disk formed differently, with more available carbon, less oxygen bonded to hydrogen, or early temperatures favoring CO2 condensation over H2O. It's possible we don't know the chemistry of every system in the galaxy. There could be environments where CO2 ice is more common than water ice. But then the question arises, why? What conditions make that birthplace so different that it flips the basic ice chemistry? Water is one of the most abundant molecules in the universe. Hydrogen is element number 1, oxygen the third. After helium, they tend to bond easily. Almost everywhere. Molecular clouds, protoplanetary disks, studied comets. Time and again, water shows up. Carbon dioxide is also common, but not as much. Carbon is less abundant than oxygen, and if it can, oxygen prefers bonding with hydrogen. The OH bond is more stable than CO at low temperatures, so seeing an 8.1 ratio favoring CO2 suggests something specific happened in Atlas's birth environment, extremely cold conditions that favor CO2 condensation, relative hydrogen scarcity in available form, or some process that removed water after formation. Loeb doesn't rule out any of these paths, but also doesn't close the door on a more uncomfortable possibility that the ratio is the result of design. If you build an object to travel between stars, you need thermal management. You want a material that absorbs and releases heat in a controlled way. CO2. Ice has different properties than water ice. It sublimates at lower temperatures and can act as a buffer against thermal changes. If you coat an artifact with layers of ice to protect it from radiation, micrometeorites, and thermal extremes, you might choose CO2 as part of that control system. It's a speculative idea, yes, but it doesn't violate any physical laws. We know solid CO2 behaves differently than water ice, can form stable deposits if conditions allow, and any traveler crossing space for millions of years would need some kind of shield against radiation, impacts, and brutal temperature swings. Still, Loeb insists on a sound principle. Don't take anything for granted. We shouldn't look at surface composition and conclude it fully explains the interior. The 8.1 ratio is rare. It needs to be noted and investigated, but it doesn't prove Atlas is natural or technological. It's another data point in a growing list of pieces that don't fit well in the standard model. Next comes the dust. As comets approach the sun, they don't just release gas, they also shed solid grains, silicates, carbon, iron trapped in the original ice. When the ice sublimates, the dust is released, forming the tail and scattering sunlight. That's why they shine so brightly, not because of the nucleus itself, but because of that huge dust cloud acting like a diffuse mirror. In Atlas, observations confirm the coma. A gas cloud, but the dusty tail appears less defined. Early images showed a diffuse glow around the object, but the long, sharp tail typical of a comet wasn't as obvious as expected. That could mean several things. Maybe Atlas is poor in dust, relatively clean ices with few silicate grains, or maybe the gas jet isn't strong enough to drag large particles. Maybe the viewing angle fools us. If the tail points away from us, along our line of sight, we'd barely see it. Or maybe simply, there isn't much dust to eject. If Atlas isn't a classic comet but something else coated with a thin ice layer, the outgassing would be mostly gaseous. The ice sublimates, gas flows, but beneath it there aren't many particles. We'd get a coma without the conventional dusty tail. Again, it's a hypothesis, but for now, it fits. Better with what's seen than the image of a giant dirty snowball. There's another chemical aspect that worries Loeb: the timing of activation. We've talked about early brightness and the mistimed green, but it's worth looking at the numbers. Atlas was detected on the 1st of July 2025 at over 5 astronomical units from the Sunday. At that distance, solar radiation is weak, about 4% of what we get on Earth. The surface temperature of a typical dark body would be around 200 degrees Celsius. Water ice at 200 degrees Celsius barely sublimates. It's practically inert. You need to get inside about 3 AU for water sublimation to be significant. CO2 ice is another story. It sublimates at lower temperatures, even near 200 degrees Celsius. If there's surface CO2, it can slowly evaporate. If Atlas is rich in CO2, its early activation makes sense. CO2 would start sublimating earlier, generating a coma and making the object visible well in advance. But what about the green glow? That hue comes from C2, diatomic carbon, produced when solar ultraviolet radiation breaks down complex organic compounds in the coma. Beyond 5 AU, the UV flux is weak and usually not enough to effectively break those molecules. The green is expected closer to the sun with much stronger UV. Atlas showed it early, way too early. So there are two paths. Either there's an internal energy source, something heating or radiating from inside that facilitates that chemistry, or the surface has a composition extraordinarily sensitive to minimal UV levels, much more than any comet observed. Both options are rare. An internal source in a natural object, the only reasonable one would be radiogenic heat. If Atlas contained appreciable amounts of radioactive isotopes like aluminum-26 or iron-60, they could provide heat, but those isotopes have short half-lives on an astronomical scale: 200,000 years for Al-26 and 2.6 million for Fe-60. If Atlas formed billions of years ago, they'd be gone, unless it's young, from a recent system where those radionuclides are still active, or unless it's not a natural object. The alternative, a surface chemistry hyperreactive to UV, is also possible. We don't know all the organic compounds that can form in other systems. There might be molecules that break down with very small doses of ultraviolet. But again, why this comet in particular? Each anomaly alone has a possible explanation. The CO2 ratio, a very cold origin. The early green, a sensitive chemistry. The weak tail, a poor dust inventory. Together, they paint a picture that doesn't fit any simple model. Loeb keeps coming back to that idea. If the dice roll 6 to 1 again and again, the prudent thing is at least to ask if the dice are loaded, not to claim it without proof, not to pass judgment, but to ask, investigate, check. Because if we assume everything is natural and never look closely, we might miss something important. And if there's a time to look under a microscope, it's now. In a few days, Atlas will skim past Mars. In a few weeks, it will be hidden behind the sun, and then we'll see if it's still here or gone. Before that, we need to talk about something else. What we don't see, the silence, the lack of coordination. Why maybe the biggest anomaly isn't Atlas itself, but how we're responding to its passage. So what exactly do we have in front of us? That's the question that keeps us awake, the one dividing the community. Some raise an eyebrow, others mock. Is Atlas a comet, an icy rocky visitor with an unlucky trajectory, or is it something more? Because when you put the pieces together and stack those supposed coincidences, a pattern starts to emerge that doesn't comfortably fit a simple explanation. Let's start with the trajectory. We said Atlas arrives aligned with the ecliptic plane, the plane of the planetary orbits, with a precision of about 5 degrees. 5 degrees, almost flat, almost perfect. Now imagine it calmly. Interstellar space is three-dimensional, with no preference for our orbital plane. An object coming from another star can come from any direction, at any inclination. There's no physical reason to respect our geometry, yet Atlas enters practically aligned, as if it knew the way, as if it had studied the map. Loeb did the math on that alignment. The probability is about 1 inch 500. Not impossible, but rare enough to pause and look twice. That's the first 6. The second is the geometry of the planetary encounters. Atlas not only aligns, it also brushes past several planets and does so at very specific times. On October 3rd, just days away, it will pass about 29 million kilometers from Mars. In human terms, that's far. 77 times the Earth-Moon distance. In orbital terms, it's a notable close approach. So notable that NASA's Mars Reconnaissance Orbiter will try to photograph it with HiRISE, a different perspective from another world. And it doesn't stop at Mars. There are relatively close passes by Venus and Jupiter, 3 planets, 3 encounters with each world situated exactly where it should be when Atlas passes. Think about it. For this to happen by chance, alignment with the plane isn't enough. You need timing. Mars must be at its orbital point when Atlas arrives. Same with Venus, same with Jupiter, and they don't wait. Mars takes almost 2 years to orbit the Sun. Venus, about 7 months. Jupiter, nearly 12 years. Their positions change day by day. Loeb calculated the combined probability that a random visitor passes that close to Jupiter, Mars, and Venus just when they're in the window. The result, 1 inch, 20,000. We're no longer talking about a single rarity. We're talking about several overlapping rarities. The alignment, about 1 inch 500, and the encounters, 1 inch 20,000. And we haven't even added size, early brightness, green glow, or mass. Taken separately, each piece admits a maybe. Someone will eventually line up, some object will have lucky encounters. But together, multiplying probabilities, the numbers get uncomfortable. Maybe the word coincidence. is working too hard. Loeb illustrates it with a simple image. You can say each roll was luck, but if the dice shows 6 to 1 again and again, at some point you wonder if they're loaded. The third 6, the perihelion date. On October 29th, Atlas will reach its closest point to the Sun, the 29th of October 2025. That same day, Earth will be exactly on the opposite side. We won't see its solar conjunction, the Sun will be between us and the object, total invisibility from any Earth-based telescope. For a random trajectory, the perihelion coinciding with our geometric blindness is another coincidence, not impossible, but unlikely. It would be enough to shift the arrival by a few weeks for the coincidence to disappear, and yet it happens. Hence the hypothesis Loeb puts on the table. It could be intentional. If you wanted to use the Sun's gravity to slow down, change course, and insert yourself into an orbit without being observed, that would be the moment. Behind the Sun, out of sight, shielded by 150 million kilometers of plasma. This is called a reverse overt maneuver. Normally, comets exploit the overt effect to gain energy. At the point of maximum speed near a massive body, a small thrust yields the greatest delta V. But it can also be used in reverse firing engines to lose energy and let gravity capture you. If Atlas performed that maneuver on October 29th, while we can't track it, it could become captured in the solar system. It wouldn't be a fleeting visitor. It would stay, orbit the Sun, and return again and again. The calendar itself adds another layer of improbability. And so we arrive at the central question, the one that splits the debate. What is Atlas? A comet? A natural object with an extraordinary chain of coincidences? Or something intentional, designed to slow down near the Sun and stay? It's not an easy question. The evidence is ambiguous and supports two narratives. You can build a case for the natural and another for the artificial. Both have strengths and weak points. That's why, before deciding, we need to zoom in, examine every layer of evidence, every number, every observation, without taking anything for granted or jumping to conclusions. Because if we always assume it's natural, we might miss something important. And if we declare it artificial without solid proof, we lose credibility. We'd be the ones crying wolf. Let's do this right. Layer by layer, fact by fact, separating facts from hypotheses without drama, or hiding the timeline transparent and honest numbers. So let's start with what's solid. The dates, the figures, the foundation on which everything else rests. The 1st of July 2025. That's the date that changed everything. The day Atlas entered our records and this story began. It was detected by the Asteroid Impact Alert System, Impact Last Alert System, operated by the University of Hawaii, hence the name Atlas. Nothing poetic, just a functional acronym. This system is designed to alert us to potentially hazardous asteroids for Earth. But it found something else, something not from our neighborhood. Something coming from much farther away. Its initial position when detected was beyond Jupiter's orbit, more than 5 astronomical units AU from the Sunday. 1 AU is the Earth-Sun distance, about 93 million miles, 150 million kilometers. 5 AU means over 466 million miles, 750 million kilometers from the Sunday. At that distance, sunlight is very weak. The intensity drops with the square of the distance. Around Jupiter, the radiation is about 25 times weaker than on Earth, just 4% of what we get here. And yet, Atlas was visible not as a tiny dot barely detectable after hours of exposure, but bright enough to immediately reveal that something was off, something unusual. Why is this surprising? Because at those distances, comets are usually dormant. They're cold and inactive, just clumps of ice and rock. They don't develop a coma, the glowing cloud of gas and dust, until much closer to the Sun, often already inside Mars's orbit. Usually, comas appear around 3 AU, but Atlas was shining at 5 AU, right where it shouldn't be. Early calculations based on that brightness suggested a size around 12 miles, 20 kilometers in diameter, 20 kilometers, bigger than Manhattan, roughly twice the estimated size of the Chicxulub impactor that caused the dinosaur extinction 66 million years ago. A visitor like that shouldn't cross paths with us so soon. In a still short search campaign, Loeb did rough calculations with the inventory of heavy elements in interstellar space, the ejection of rocks from planetary systems, and the fraction that passes near us. An object that size should appear on average once every 10,000 years. Just once every 10,000 years. And we've only been searching systematically for a few decades. A bit more if you count the years before modern techniques. So we've already encountered a case that statistically should appear once per century after century. Strange. Not impossible, but strange. Also, before Atlas, we'd only seen 2 interstellar visitors, Oumuamua in 2017 and Borisov in 2019, both small. Oumuamua was about the size of a football field, Borisov a few hundred meters. Here the power law applies that governs many natural populations. For every big mountain, there are billions of rocks, and for every rock, billions of pebbles. The physics of formation and ejection of bodies suggests that statistically, we should encounter thousands of small objects before seeing a giant. Loeb estimates about 100,000 bodies the size of Oumuamua should have appeared before something like Atlas 100,000, and so far we've seen 2. You might rightly object that our methods have biases. Small and dark objects slip away, big and bright ones get caught. But even allowing for that bias, there's one detail. Atlas shouldn't have been that bright. At the distance where it was detected, let's go back to July 1, beyond Jupiter, weak light, usually dark objects, Atlas was shining. And that opened the first serious question. What was heating it? The obvious answer is the sun. But at 5 AU, the available energy usually isn't enough to inflate a large bright coma. The surface temperature of a typical dark body there is around 200 Kelvin -100 degrees Fahrenheit. At that temperature, water ice barely sublimates, it's almost inert. For H2O to start evaporating vigorously, you have to get closer to about 3 AU or less. However, there is another ice, CO2, carbon dioxide, which sublimates at lower temperatures, even near 200 Kelvin -100 degrees Celsius. If there's surface CO2, it can slowly evaporate. If Atlas is rich in CO2, early activity fits the CO2, would start sublimating earlier, creating a coma and making the object visible well in advance. Then there's the green glow. A few weeks ago, data reported 48 hours before an interview with Loeb showed a pale green in Atlas's spectrum. In comets, that color usually comes from diatomic carbon C2, solar ultraviolet radiation, breaks down complex organic molecules in the coma, and produces C2 fragments that emit green light. That alone is normal. What's unusual is the timing. At 5 AU, the UV flux is weak and usually doesn't break down those molecules effectively. Seeing green so early is another rarity. Not impossible, but uncommon. On top of that came a mass update. At least 33 billion tons. That sounds huge, but it's worth putting in context. If the diameter really were 20 kilometers, and we assume a typical comet density of 500 kilograms per cubic meter, the mass would be around 1 trillion tons, 1 x 10, circumflex 12 tons, or 2 trillion in European scale, far above 33 billion tons. So 33 billion would be too little for a 20 kilometers nucleus made of porous, not dense ice. For 20 kilometers and 33 billion tons to fit, the material would have to be extremely light or the nucleus much smaller than assumed. Conversely, if the body were rocky or metallic 3,000 to 5,000 kilograms per cubic meter, the expected mass for 20 kilometers would be even greater, not less. Here, parameters need better calibration. In any case, If Atlas had an unusual mass for its apparent size, its gravitational pull could leave measurable traces, tiny perturbations in the orbits of Mars, Venus, or even Earth during close approaches. Detecting those would confirm the mass. Not detecting them would invite revising the model. Mass doesn't exist in a vacuum. It adds up to everything else. 20 kilometers estimated diameter, brightness beyond 5 AU, early green glow, alignment with the ecliptic within 5 degrees, and close passes by 3 planets in very specific windows. Each isolated data point allows a plausible explanation. A different density, CO2 explaining sensitive surface chemical activity, pure coincidence in geometry. Together, the picture fits any simple model. So we reach October 3rd. In a matter of days, the close encounter with Mars will happen. Atlas will pass just 18 million miles, 29 million kilometers from the red planet. That's 0.19 AU on an orbital scale, a close shave. NASA knows this. The Mars Reconnaissance Orbiter will try to photograph it with its high-resolution camera. A valuable opportunity to see Atlas from another world, from another perspective, with high-resolution images that could reveal structure, shape, maybe localized jets. If it's a comet, we'd expect a diffuse coma, a bright nucleus in the center, and gas jets emerging from specific areas, as the manual says, when an icy nucleus heats up. If it's something else, we might see geometries that don't fit with an irregular rock covered in dirty ice. This is finally a direct test, the first chance for solid visual data, and it's coming soon. Then comes October 29th, and that day everything will change. Now it's time to compare what was supposed to happen with what's actually happening. Here's where the classic script of "it's just a comet" starts to crack under the weight of observations. When astronomers discover a new comet, there's an unspoken manual, expectations built from decades of data, hundreds of comets studied, thousands of measurements. We know generally how they behave and what to expect. Expectation 1. Inactivity in the cold beyond 3 AU from the Sunday. Dim light, extreme temperatures. Comets are usually dormant, no gas emission, no bright coma, just dark lumps of ice and rock floating silently. The coma requires sublimation of water ice, H2O, and that needs heat. Typically, intense sublimation doesn't happen much beyond Mars's orbit. Reality, Atlas wasn't dormant. It shone brightly enough to be easily detected, and therefore, for astronomers to immediately infer an unusual size to justify so much light at that distance. You can try to save the model. Maybe it contains very volatile ices like N2, CO, or CO2 that sublimate at lower temperatures. Borisov, the second interstellar visitor, showed CO in its spectrum and activity at great distances. CO sublimates even in deep cold. Maybe Atlas is similar, rich in CO or CO2, explaining the early brightness. Expectation 2. Random arrival angles. Interstellar objects can come from any direction, with any inclination. Our orbital plane, the ecliptic, is our local geometry. There's no physical reason for a stranger to respect it. Oumuamua came with 20 degrees inclination relative to the ecliptic, Borisov with 40 degrees. That's what you'd expect, random, no correlation. Reality. Atlas comes in with practically zero inclination, almost embedded in the disk where our planets orbit. Loeb estimates the probability of such a close alignment by chance at about 1 in 500. Not impossible, but rare enough to pause and think. And this is the third detected visitor, so one arriving almost exactly in the plane draws attention. Expectation 3. Few close encounters with planets. Space is huge. Planets are small. For a random trajectory, passing close to one planet is already unlikely, and doing so with several is much rarer. Reality. Atlas passes close to Mars, Venus, and Jupiter, not just spatially close, but also temporally. Each planet is in the right part of its orbit when Atlas passes. Mars takes 687 days to orbit the Sun, Venus 225 days, Jupiter almost 12 years. Their positions change daily. Still, on October 3rd, Atlas passes 18 million miles, 29 million km from Mars, and there are useful alignments with Venus and Jupiter too. Loeb calculates the combined probability of such a triple coincidence at about 1 in 20,000. Again, not zero, but it starts to get uncomfortable when piled up with everything else. Expectation 4. The green glow appears near the Sunday. The typical green glow shows up when ultraviolet radiation breaks down complex organics in the coma and produces diatomic carbon C2 that emits green light. It's usually seen clearly within 3 AU, where UV is intense. Reality. Atlas showed green emission beyond 5 AU near Jupiter, where UV flux is just 4% of Earth's, too weak to break molecules effectively. Loeb highlights the rarity and suggests two possibilities. Either the surface chemistry is extraordinarily sensitive to weak UV, much more than any known comet, or there's an internal energy source providing heat or radiation. For a natural object, that source would be radiogenic heat, but typical isotopes like Al-26 and Fe-60 have short half-lives on cosmic scales. Titanium-44 and other isotopes have half-lives of a few decades to a few hundred years. If Atlas formed billions of years ago, it shouldn't still be warm unless it comes from a young system or isn't a natural object. Loeb doesn't make categorical claims, but doesn't close that door either. If someone designed an interstellar traveler, they might coat it with ice for protection, thermal management, and camouflage. Sublimating near a star, it would look like a natural comet at first glance, until you get close, do the math, and ask why this chemistry, why this timing, why this geometry. Add early brightness where it should be dormant, near zero inclination, 3 close encounters, a 1 in 20,000 chance, green glow too early. Each piece alone has a reasonable explanation, but altogether start to look like too many coincidences. That's where we stand, not to deliver verdicts, but to ask the right questions and organize them. And those are exactly the questions we're raising now. For a moment, everything seemed to fit. The normal comet story held up. The anomalies seemed explainable. The numbers fit. Atlas has a coma that's confirmed. A diffuse, extended gas cloud surrounds the object, exactly what you expect from an active comet. The spectrum supports it: water, carbon dioxide, and possibly carbon monoxide. There's also a tail, not spectacular, not the fan-shaped one in famous photos, but material flowing outward, signs of outgassing. And this matters. If Atlas were a purely solid or metallic technological object, we probably wouldn't see any of this. No coma, no tail, no gas lines vaporizing for a while. The simple explanation seemed enough. Atlas is a very large, very unusual comet, with rare chemistry and an uncommon trajectory, but still natural. On that basis, models began to take shape. If Atlas is rich in CO2, early activity makes sense. CO2 sublimates at lower temperatures than water. With a surface layer dominated by that ice, outgassing could start beyond 5 AU. Early brightness would no longer be a mystery. Plus, enough escaping CO2 would inflate a broad coma that scatters sunlight and makes the whole thing look bright even if the nucleus isn't that big. Hence the hypothesis, and it makes the whole thing look bright even if the core isn't that big. Hence the hypothesis. Maybe the initial 20 kilometers estimate is too high. Perhaps the core is 10 kilometers and the rest is coma. That would ease the size problem. We wouldn't have seen a giant, but a moderate comet with a lush halo. The green color could also fit into this picture. A surface with organics especially sensitive to ultraviolet radiation would produce CO2 earlier than usual. And if Atlas formed in a protoplanetary disk with different abundances, the starting chemistry would change too. It's not impossible. The chemistry varies with the star and the formation temperature. The geometry in this story is accepted as chance. Someone had to be first. Over time, objects almost coplanar with the ecliptic will appear. For one to arrive so early is unlikely, not impossible. The same with rare planetary encounters, yes, but space also has gusts. If you flip a coin 1,000 times, sometimes you'll get 10 heads in a row. For a moment, the whole set held together. All the strange pieces fit if we accepted a chain of unlikely events. And then, non-gravitational acceleration came into play. Or rather, its absence. When a comet outgasses, the jet acts like a tiny engine. It pushes and slightly deflects the trajectory. That small but measurable thrust is one of the classic signs of activity. A MMOM showed such a deviation, no visible coma, no tail, no clear gas lines. That mismatch led Loeb to propose a possibility. Technological acceleration without apparent outgassing sounds hardly comet-like. Unless there's a solar sail, some other mechanism, or something we don't yet understand. Borisov was the opposite. Obvious tail, textbook comet spectrum, and non-gravitational acceleration. Consistent with its outgassing. Everything fit, it was the quintessential comet. And Atlas, yes, it has a wide coma and is releasing gas and dust. It should show additional thrust. However, so far no significant non-gravitational acceleration has been detected. The trajectory seems to obey only the gravity of the sun and planets. No net thrust, that's odd. A large coma suggests enough gas flow to produce brightness. And also a measurable push. Conservation of momentum doesn't rest. You eject mass. In one direction, you move slightly in the opposite. If the thrust doesn't appear, only narrow escapes remain. Such a weak escape that it falls below detection threshold. Very symmetrical jets that cancel out. Brief episodes hidden by the average effect. Possible, yes. Fine-tuned too. It's the pattern repeated every time we save an anomaly. The solution calls for fine-tuning. Activity far from the sun, uncommon volatile ices, or very sensitive chemistry. Premature green, atypical organics, or internal energy. Alignment with the ecliptic, luck 3 encounters in a window, plus luck high or low mass. Depending on the reading, different density or actual size, large coma without notable thrust. Almost ideal jet geometry. Each piece separately can be explained. But the whole demands stacking several low probability assumptions at once. And just when that tower seemed stable, new numbers arrived. 48 hours before the interview, Loeb updated the mass estimate at least 33 billion tons for a 20 kilometers body made of cometary ice. 500 kilometers MP3, you'd expect around 2. Schemmel, 12 tons. 2 trillion in long scale. The new figure is 60 times smaller. That implies either Atlas isn't that big, or the material isn't dirty snowball ice, or both. If the 33 billion were correct, and the diameter really was 20 kilometers, the average density would be Mauri Pirocco Kilpetereo, lighter than many foamed materials, too porous even by cometary standards. Another option is shape. An elongated body like a smoke plume, bar, or disk would reduce effective volume and raise apparent density. Or simply the initial size was overestimated, and the brightness mainly comes from the coma, of course. The uncomfortable possibility that it's not a typical comet. With that data, the apparent coma dissolved, the momentary clarity clouded again, and we return slowly, taking deep breaths, to the zone of uncertainty. The only place where important questions really get answered. 48 hours before the interview, that's when everything started to crack. The carefully built narrative around a natural comet stopped holding up. The numbers stopped fitting. The updates came quietly, no headlines. A parameter update, new figures in a table. And yet they changed the whole picture. mass at least 33 billion tons. That qualifier matters. At least sets a floor, not a ceiling. 33 billion is the lower limit. Reality could be higher. Then the green glow, not just its existence, but when, how much, and where it appeared, was detected when Atlas was still beyond 5 AU, right in a domain where the sun's ultraviolet light is weak and most comets remain cold, chemically dormant, discrete. Still, the glow was there, sharp, unmistakable green. That doesn't fit the usual. At that distance, the green emission from diatomic carbon CO2 requires energy, a V-flux, capable of breaking complex organics in the coma beyond 5 AU. That flux is about 0.4% of Earth's, too little for vigorous photodissociation unless the chemistry is extraordinarily sensitive. Unknown molecules that break with a minimal touch of V or a second energy source exists. Loeb returns again and again to that point. Internal energy, something inside providing heat or radiation and activating chemical processes that shouldn't be so effective in the cold. In a natural comet, the menu is short: radiogenic heat. Isotopes like aluminum-26 or iron-60 forged in supernovae could do it if still present, but their half-lives are short, astronomically speaking, atiratiu keriton yateo 6 years. If Atlas formed billions of years ago, that heat shouldn't exist anymore. For it to exist, Atlas would have to be young, formed less than a few million years ago. Maybe less than a million, that is, from a recent system with fresh material enriched in radionuclides. It's possible. Not impossible, but it adds another specific condition to a list that already demands several coincidences, and the unsettling implication appears. If Atlas already has enough internal heat to drive surface chemistry at 5 AU, what will happen when it gets closer to the Sun at perihelion at 3 to 3.5 AU? The solar flux will be 100 times stronger than where it was first detected, taking 5 AU as reference. The surface temperature will skyrocket. If it's already active far away, how will it respond to heat? In a normal comet, we expect more of the same. More outgassing, longer tail, increased brightness. Typical behavior approaching the Sun. But if there's also an internal source, perihelion could bring something unexpected by the standard model. That moment is October 29. Behind the Sun, out of view, just when we're blind, Loeb calls that stretch the maneuver window. The ideal moment to change trajectory without witnesses. If you wanted to use the Sun's gravity to slow down and enter a bound orbit, perihelion is the spot of maximum speed, deepest gravitational well, the point where a small dive yields the greatest effect. It's the overt maneuver. Spacecraft have used it for decades. Voyager, Cassini, Juno ignite engines where energy efficiency is optimal, usually to speed up. Loeb suggests the mirror, a reverse overt maneuver. Use perihelion to brake, lose energy, and let gravity capture. The physics is the same. Slowing down at perihelion is much more effective than elsewhere in the orbit. If you want it to stay, that would be the smart move. The calendar adds more than efficiency. It adds concealment. October 29. Earth will be on the opposite side of the Sun-solar conjunction, the solar disk. Hundreds of 50 million kilometers of plasma between us and the object will block any observation from Earth. A blackout. If someone wanted to execute a maneuver without witnesses, without light curves or spectra revealing what's happening, this would be the time and place. That perihelion coincides precisely with our blindness is another unlikely piece stacked on the previous ones. It would be enough to vary the speed a bit, advance or delay arrival by a few weeks, so the geometry changes, and we could observe the perihelion passage. But we won't this time. No, Loeb doesn't claim intentionality, doesn't assert. He asks, how many coincidences do we accept before questioning if they really are? Alignment with the ecliptic. Malcho 500. Encounters with 3 planets. Pamela 120,000. Early activity, early green. Mass that doesn't add up, chemistry that clashes, and now timing that places perihelion. When we can't look, if you roll dice and get sixes over and over, sooner or later you wonder if they're loaded. That's the metaphor. Loeb repeats not as accusation or conclusion, but as an invitation to check. Because if we take for granted that everything is natural and never look closely, we might miss something important. And those new figures, those 33 billion tons, along with an off-schedule green, made Loeb see a pattern less comfortable with the conventional comet idea. It's not proof. The data aren't conclusive, but they're strange enough and compatible with the possibility of design to deserve serious investigation. That's where the collapse of the comfortable narrative is understood, the moment we accept that maybe we don't fully know what we're looking at. Because if Atlas isn't a comet, if it's something else, everything changes rules, expectations, implications. And the most unsettling thing isn't the hypothesis itself, but that we're about to lose the best chance to check it. In a few days, Atlas will hide behind the sun. If it returns, only the trajectory will tell the story. If it reappears on the same hyperbolic path and moves away, it was probably a rare comet. Difficult but natural. If instead, it returns on a bound orbit, if its path has changed, and it's trapped in the solar system, the questions will be different, more demanding, less comfortable. All that will be decided soon, quietly, in the dark. Behind the sun, now we have to talk about failure, not Atlas's failure, ours. A failure of coordination, preparation, reflexes. The uncomfortable truth is simple. We had months to organize and didn't. Atlas was detected July 1, almost 4 months until perihelion. 4 months to organize a global campaign. Align telescopes, distribute observation windows, agree protocols, and ensure nothing essential slipped by. That didn't happen. There was no coherent international campaign, no joint effort by major agencies, no unified plan to share observations. Before Atlas disappeared behind the sun, instead, loose pieces. JAVEL looked. James Webb looked. Several ground observatories too, each team on its own, each with its data and preprints. There was no real-time synthesis, no urgency, and that hurts most, the lack of rush when rush was needed. If Atlas ends up being just a comet, fine, there will be data, lessons, curiosities, but if there's even a small chance it's something else, then we miss the most important opportunity in modern astronomy. Loeb has repeated it publicly for weeks. Coordinated observations, a plan, seriousness are needed. The dominant response has been silence. Some mocked, others ignored it. Many said he exaggerated, sought attention, saw patterns where there were none. Meanwhile, no one set up the campaign he asked for. To be fair, organizing international observations isn't easy. Telescopes are scheduled years in advance. Time is competitive and precious. You can't say, stop everything and look at this without very strong justification. For many, Atlas's anomalies weren't urgent enough to rearrange agendas. Interesting, yes. Worthy of study, sure. Revolutionary, urgent, no, they weren't convinced. There's also a bias, not the classic confirmation bias, but its conservative reflection, preferring the simplest, safest, most familiar explanation. Probably it's a comet, no need for anything exceptional. That bias costs opportunities, data, knowledge, because even if it's just a comet, it's still extraordinarily unusual. The largest interstellar visitor detected, rare chemistry, unlikely geometry, properties still not fully fitting. That alone would justify serious coordination. But it didn't happen, and now the calendar runs. October 3. Atlas will pass near Mars. Mars Reconnaissance Orbiter will try to photograph it with HiRISE. It's a valuable window, but only one spacecraft, one camera, a single viewpoint. We could have had multiple platforms pointing from different geometries. The entire arsenal available in the inner solar system. We didn't do it. October 29, it hides completely behind the sun. Out of reach of any ground telescope, there will be a period of weeks, maybe a month, without data. A blind stretch. We won't know what's happening. If anything changes, if there's a maneuver, we'll just have to wait. When Atlas reappears on the other side, in late November or early December, we'll reconstruct the story only from its trajectory. We'll measure positions, adjust the orbit, and see if anything changed. If it stays on the hyperbolic path, if it keeps escaping, probably nothing dramatic happened. A strange but natural comet. If instead the orbit becomes elliptical, if it's bound to the solar system, we'll have to explain how comets don't get captured on their own. With hyperbolic velocity, you leave with hyperbolic velocity, conservation of energy. Unless something changes your energy, you lose speed, there's a maneuver. Outgassing can modify trajectories, yes, but to turn a hyperbolic orbit into elliptical would require massive outgassing, much greater than seen so far, significant mass loss, ejection of tons in a very specific direction, and clear signs of it. Huge tail, enormous coma, pronounced brightness changes. If that trace doesn't appear and it still reappears bound, the natural explanation narrows. In this context, Loeb proposes his Loeb scale, analogous to Rio's contact claim scale or Torino's impact risk scale, 1 to 10 to gauge how seriously to consider an artificial origin. 0 is natural, of course. 10, definitive, artificial. Most objects, 0. Paralop. Yellow smoke hovered around 5 to 6 anomalies. Non-gravitational acceleration without coma. Strange shape, intriguing but inconclusive. Atlas, before recent data, would be at 4 to 5. After mass update and early green, it rises to 5 to 6, maybe more. It's not a 10, no signals or transmissions, no structures, no mistakes, but high enough to deserve serious investigation, international coordination. Not structures, no mistakes, but high enough to deserve serious investigation, international coordination, and treatment as a possible historic event. That treatment never came. There wasn't the urgency the case deserved. Loeb calls it a failure of imagination, curiosity, and willingness to consider uncomfortable scenarios. Science must follow the data wherever it leads, not dismiss hypotheses because they make us uncomfortable. The idea of an artificial atlas is unsettling, and if true, it means we're not alone, that there are civilizations out there with interstellar travel technology, that they've found us, or at least sent probes. These are huge claims that demand extraordinary evidence. Carl Sagan said it best: extraordinary claims require extraordinary evidence, and he was right. Loeb adds that it also takes extraordinary curiosity to seek out that evidence. If we don't look, we won't find. If we don't test, we can't confirm. By not coordinating a campaign up to the challenge, by not treating Atlas with the urgency its anomalies suggested, we've chosen to look away. And choices have consequences. If Atlas is natural and we treat it as potentially artificial, the worst case is spending some telescope time and gaining understanding of a rare object, little to no harm done. But if Atlas is artificial and we treat it as natural without a close look, we lose the most important opportunity in human history. The first evidence of another intelligence is an asymmetric risk. The cost of a false negative far outweighs that of a false positive. And here we are, just days from perihelion, with no coordinated plan, no unified effort, just scattered observations and the hope that, with luck, someone will catch the essentials. It's a failure of coordination, ambition, and courage to ask the hard questions. Now we'll pay the price of silence and of looking away when we could have observed as the sun's shadow approaches. We lower our voices. There's little left to say and much to verify. When Atlas returns, its orbit will bring the answer. Until then, we take a deep breath and let the sky run its course. Now, we're here. At the lowest point in the stretch of greatest uncertainty, the patient construction has cracked, and we're left with fragments, questions, shadows. The 29th of October 2025, that date closes in on us, not as a promise, but as a void, a gap in knowledge, a moment when what we know stops and what we don't yet understand begins. The naked truth is simple. We'll only see before and after. There will be no live signal from perihelion, no real-time coverage, no dramatic moment we can witness. There will be silence. The sun will be between us and Atlas, 93 million miles of burning plasma, a wall of light and radiation. Any Earth-based telescope pointed that way will see only the blinding glare of our star. There's no practical window through that brightness. No technical trick can open it from here. When something is right behind the sun in our line of sight, it's hidden. Period. We have spacecraft in the solar system that could theoretically look from other angles, the Parker Solar Probe, which orbits close to the sun, but its geometry won't give it a line of sight during perihelion. The Mars rovers will have their chance on October 3, not the 29th. Juno's at Jupiter, too far to offer the needed perspective. JUICE is in transit and won't be in position either. Ephemerides have been checked, geometries crossed, and the answer repeats. No one will be watching. No one will be able to watch. If something happens, it will happen in private, out of focus, without witnesses. That's what makes this moment so hard. Not just that we ignore what's about to happen, but that we won't know what happened until weeks later. We'll have to wait for reappearance, measure the new trajectory, reconstruct backwards, infer. Fill in the silences like an audio cutoff at the key phrase. We hear the beginning, we hear the end, but the center, the part that gives it all meaning, goes silent. And, in that silence, anything fits. If Atlas is a comet, it will pass perihelion like many others. More heat, more outgassing, maybe more brightness, maybe a longer tail, maybe some fragments if the nucleus weakens. But the orbit will remain essentially the same. It arrives at hyperbolic speed and leaves at hyperbolic speed. It will pass by and continue its journey through the galaxy. By late November, we'll watch it recede, tracking it for weeks or months until it fades into the noise. And that will be the end. A strange, memorable visitor, but a comet after all. But if there's intent behind its path, October 29 would be the moment that intent reveals itself. Any planned maneuver would happen then, at perihelion maximum efficiency, total privacy. And over Timverse ignite engines, deploy sails, shed mass, whatever counts as propulsion for an interstellar traveler, slow down, lose orbital energy, let the sun's gravity finish the job, and fall into a bound orbit. If that happens, when Atlas reappears, we won't see it escape but return an ellipse, a body captured in our neighborhood. Not a visitor, but a resident. Maybe forever or nearly so. Depending on parameters, it would return to perihelion in years, decades, or centuries. But it would return again and again. And that changes everything. Love has pointed out an even more speculative scenario. It sounds like science fiction, but is physically possible. What if Atlas isn't the probe, but the carrier? Think about how we explore. We rarely send a single monolithic craft. We prefer a robust mothership that survives the journey and, upon arrival, releases specialized probes. That's how we did Cassini-Huygens. That's how we coordinate orbiters and landers on Mars. Diversifying is safer. And, if Atlas did that, during perihelion, just when we can't look, it could release daughter probes, the size of a car, a washing machine, maybe smaller, too small to detect instantly, able to scatter in different directions without raising. Suspicion some toward Earth, others to Mars, Venus, Jupiter's moons, asteroid belts. By the time we saw them, if we ever do, they'd already be in position, observing silently. Loeb doesn't present this as the main prediction, only as a possibility to watch for, because if it happens, tracking small, fast objects will be harder than following Atlas. It will require patient attention, and they could be anywhere. So, what do we do now, in this valley facing a void we can't fill? The only sensible thing is to prepare for what comes after. If perihelion is inaccessible, at least we can be ready for reappearance. Coordinate observations for late November, reserve telescope time, align teams and analysis protocols, so when Atlas shows up again, we don't lose a single piece of data. We'll need to measure positions with the utmost precision, adjust the orbit rigorously, look for any change, a non-gravitational term, a different eccentricity, a velocity variation, any trace that doesn't fit a simple hyperbolic pass. And we'll have to look for signs of daughter probes if they were released, subtle traces, a brief dip in brightness from mass loss, strange radar echoes, tiny dots separating on their own trajectories. It's wise to watch the inner planets Earth, Mars, Venus, for any new objects in low or mid-orbit, check catalogs with filters for unusual movement, inspect meteor and seismic databases on Earth, and if any Martian station inherited from InSight is still operational, monitor there too for minimal impacts or soft landings. Serene vigilance. Curiosity without rush, eyes wide open. If something extraordinary happens, it won't come with fanfare. It will come in the data, in small anomalies, easy to overlook if you don't look closely enough. That's the plan. Wait, observe, analyze, search. Don't take anything for granted. Don't dismiss prematurely. Look with the greatest care, precision, and honesty. Maybe we'll find something, or maybe nothing. Maybe Atlas is a comet, and these guesses won't go beyond guesses. We won't know without trying. We won't know if we don't dare to ask the question and calmly pursue the answer. And it starts now, at the bottom of the abyss where uncertainty is greatest and knowledge minimal. From here, there's only one way: up, toward the light, toward answers, toward truth, whatever it may be. Let's be honest, completely honest, without dramatizing or exaggerating data on the table and two competing interpretations to explain it. In the end, it all comes down to one simple, huge question. What is Atlas? A natural comet or an artificial probe? Two main hypotheses, each with pros and cons. Let's start with hypothesis A, natural comet. Its strengths are clear and observable. There's a coma, a gas cloud surrounding the object. Spectra show water, CO2, and possibly CO, chemical signatures typical of sublimating ices. There's also evidence of a tail not spectacular, but with structure and outward material flow, exactly what you'd expect from an active comet. Also, no non-gravitational acceleration, contradicting the purely orbital model, has been measured. The trajectory fits, for now, with the sun's pull. And small planetary perturbations, no mysterious pushes. All this forms a solid block, supporting comet-like behavior. So why does doubt persist? Because of the weaknesses that have accumulated. Early brightness. Atlas was visible beyond 5 AU, where sunlight is weak and most comets are inactive. To explain this naturally, you'd need very volatile ices, CO2, CO, maybe N2, that sublimate at low temperatures. It's possible, Borisov showed CO, but it's uncommon. Premature CO2 emission appeared when Atlas was still far out, in a low-energy regime. You'd need extremely sensitive surface chemistry, or some internal energy source. Unusual, yes. Also, the CO2 to H2O ratio is 8.1, inverted compared to most water-dominated comets, forcing us to invoke very specific formation conditions, different chemistry, colder environments, peculiar thermal history possible, but another atypical piece. Alignment with the ecliptic, almost flat orbit. Estimated probability 1 in 500, not impossible, but unlikely. 3 planetary encounters, Mars, Venus, Jupiter, in a narrow window, orbital positions just right when Atlas passes. Combined probability 1 inch 20,000, another tough odds. Perihelion on October 29, just when Earth is in conjunction and we can observe. Another low probability coincidence. Plus, a mass of 33 billion tons high for typical comet sizes and densities, forcing adjustments to size or density, or both, thus tweaking the model and statistical expectations. By power law, objects Atlas's size should be very rare. We'd expect to have seen tens of thousands smaller ones before. Yet before Atlas, only 2 interstellar visitors were detected. The count doesn't add up well. Each point can be saved with specific natural explanations, but the whole requires stacking several low probabilities at once. It's not impossible, but statistically uncomfortable. So that's the summary of Hypothesis A, natural comet with many peculiarities. Now let's move to Hypothesis B, artificial probe. Its strengths are less observational and more about internal consistency. Being almost in the ecliptic plane makes sense if it was designed to study planets. It facilitates flybys and observations. Multiple encounters with Mars, Venus, and Jupiter fit if gravitational assists were planned. Perihelion during Earth's blind spot is logical if privacy is sought for a maneuver. The idea of an over-timverse breaking at perihelion to become bound is physically sensible and energetically optimal. The unusual surface chemistry could be read as designed protection CO, too rich ice for thermal management, radiation shielding, camouflage. Early brightness would match internal energy in operation, and the lack of strong non-gravitational thrust would be compatible if the coma is secondary, and the body isn't essentially a block of ice. Everything fits under one central assumption: intentional design. But here the weak points are big. It's an extraordinary claim: extraterrestrial intelligence, interstellar travel technology, probes operating here and now, and extraordinary claims require extraordinary evidence. There's no direct evidence of artificiality, no transmissions, no signals, no obvious constructive geometries or materials. What we have are anomalies and interesting coincidences, yes, but not conclusive. For every anomaly there's a natural way out, though rare or requiring fine conditions. Occam's razor asks us to prefer the simple. Alien probe isn't simple. It's an explanation loaded with chained assumptions: existence, technology, motivation, arrival, operation, too many links that could break. Where does that leave us? Loebno doesn't give a verdict. On his scale, he places Atlas at 5.6 out of 10, anomalous enough to warrant serious investigation, open enough not to dismiss, but insufficient to declare it artificial. It's the middle ground of honest uncertainty. That honesty matters because error lurks on both sides. We can be gullible, see patterns in the fog, jump to conclusions, shout aliens at every oddity, and lose credibility. Or we can be ultra-skeptical, dismiss uncomfortable hypotheses without a close look, assume everything is natural, and miss discoveries. Both extremes impoverish knowledge. The reasonable path lies in the middle: curiosity without credulity, skepticism without dogma, considering unusual hypotheses but demanding solid proof. Translated into action: observe carefully, gather rigorous data, analyze honestly, avoid free assumptions, and resist premature dismissal. Very soon, we'll have new clues. We'll know what orbit Atlas takes after perihelion, if anything changed, if the data tips the scale toward A or B. Until then, we live with doubt, with two open possibilities, and a question that answers itself not with opinions, but with measurement in the coming days and weeks. The data will tell, not speculation, not belief, but observation, and that's the only right way to do it. We've reached the end, the resolution phase, the point where the lines cross and we finally glimpse what it all means. Beyond which hypothesis turns out true, a deeper truth emerges. one that speaks about us, about our civilization, and how we react when the universe throws something that unsettles our expectations. Atlas isn't just a rare case of dynamics and chemistry. It's also a mirror, showing us habits, reflexes, and limits we'd rather not see. That mirror says calmly but clearly that we weren't ready. We weren't ready to coordinate, nor to respond quickly, nor to treat anomalies with the urgency they deserved before the clock ran out. We had 4 months between discovery and perihelion, a precious margin that was underused. We lacked a truly global campaign, failed to mobilize resources at scale, and lacked a unified plan to not miss any window. What we had were valuable but scattered efforts, without a live synthesis in real time. It's not a reproach to anyone in particular, but a diagnosis of the system. And honest diagnoses help improve things. The causes are many and understandable. Telescope schedules booked years in advance, budgets influenced by administrative inertia, and rhythms that are, by definition, cautious. Still, there's a deeper factor worth naming, a kind of fear. Fear of being wrong, of seeming gullible, of proposing something extraordinary only for it to turn out ordinary. In science, there's also pressure to provide a safe, familiar explanation, to not stand out too much. That pressure cools curiosity and reduces the willingness to explore uncomfortable ideas. And when curiosity cools, so do opportunities. Loeb knows this climate firsthand. When he suggested a moi might be artificial, he faced ridicule and labels. Yet his questions are legitimate, his calculations well laid out, and his method scientific. He might be wrong in his conclusion, but not in asking questions. Questioning and challenging assumptions is what pushes the frontier of knowledge. Looking where others don't isn't a whim, it's part of the job. If there were a civilization out there sending probes, how would we recognize it without a neon sign? It won't speak our frequencies or follow our aesthetic script of technology. It would show up as an anomaly, a set of unlikely traits that together demand a different interpretation. Exactly the kind of pattern we see in Atlas, with coincidences that, when combined, strain the simple model's seams. Systematically refusing to look closely because it's probably natural would blind us to what we say we're searching for. Good practice is to observe first and judge later. That's why this moment is critical not just for Atlas, but for the precedent we set. From here come protocols, reflexes, and working methods for the next time the sky surprises us. Soon, we'll have data tipping the scales. No shouting, no rush. Verification will come from positions, ephemerides, and orbits, not opinions. Calmness here is a tool. If on reappearance it keeps a hyperbolic orbit, the most reasonable conclusion is it's a natural comet. Rare, anomalous, statistically uncommon, but a comet nonetheless. Still, it will teach us about chemistry, activity at great distances, and detection biases. It wouldn't be a failure, just knowledge put in its place. Later, we'll simply wait for the next interstellar visitor. But if instead it reappears in an elliptical orbit and stays bound to the sun, the game changes visibly. We'd have to explain how an escaping object became a resident without clear signs of extreme processes. Outgassing can cause deviations, but turning a hyperbola into an ellipse requires losses and phenomena that should have left a notable trace. If that trace doesn't appear, the artificial hypothesis gains relative weight. It's not proven, but it stops being remote. From there, more demanding and unprecedented practical questions arise. If Atlas were artificial and sought capture, what would it do next? Observe, transmit, release smaller probes, stay silent? What stance would we take? Cautious communication, dedicated mission, or patient and respectful surveillance? There's no consensus-approved manual for such a situation. It would be a slow, responsible global conversation, demanding more data than opinions. The implications go beyond technology and touch layers and waves of human experience. Changes like this reorder philosophy, religion, politics, and culture, not by imposition, but by new context. Understanding that we're not the only intelligence on the cosmic map reshuffles old questions, sets new priorities, and redefines what it means to be up to the task as a species. But we're not there yet. We're still in the antechamber. The immediate schedule is sober and clear. October 29, perihelion and silence behind the Sunday. Then weeks of waiting until late November or early December when it reappears. Then astrometry will speak again. Fine measurements, orbital adjustments, and comparison with predictions. From that crossing will come the operational answer without fireworks. That's how it should be. At that moment, we'll know if the guest left or stayed. We'll know if the solar system has a new neighbor, and if our species' story just turned a page, or if it was just a strange, memorable comet, and our tools worked as they should. Either outcome adds value if viewed calmly. The key is not to force the interpretation too soon. Both paths teach something important and complementary. If it's natural, the universe turns out even more diverse and reminds us that taxonomies remain incomplete. We learn about comet formation in other systems and how instruments bias our view. If it's artificial, the whole framework changes and opens a new chapter demanding caution, cooperation, and patience. In either case, we win if we keep a cool head. One last question gently bounces back to you. Where will you be on October 29? Knowing something's happening behind the sun, even if you can't see it? What kind of evidence would you consider enough to accept it's not just a comet, a bound orbit, coherent signals, release of smaller objects? What data would make you say this deserves another category? It's healthy to think about this beforehand, so you don't decide in the heat of the moment. A prepared mind listens better. The universe is vast and ancient, and sometimes it speaks to us in numbers, trajectories, and light. Atlas is one of those questions posed with equations and silences. Soon, we'll have an answer, and with it, a lesson. When the guest doesn't leave, it becomes a neighbor, and each of us decides what that means. Until then, we count backward, take a deep breath, and keep our curiosity alive.